Yeah, let me start. And good morning. My name is Junho, and I'm a research engineer at SK Telco R&D Center. And and our team was established in 2017, and we are grouped together to address cost-effective way to monitor telco infrastructure with open source open hardware like OCP gears and open source software such as we are using the DPDK and Hadoop and Spark. And we are working on the DevOps network visibility solution for starting from the data center network to mobile network. And back to 2016, our infrastructure operation team in SK Telecom was evaluating vendor solution to adopt for network monitoring, such as Gigaman NetScout Extra Hop. But as you know, it needs a high-level decision because it needs a multi-million-dollar investment per year. But as you know, the year-to-year, the capex and opex decrease while scale up the infrastructure to monitor is still increase as network traffic exponentially increase. So, sorry. So every year the spend for vendor solution is, I think, not a sustainable way in SK Telecom. So also, the most enterprise except the hyperscaler, because they have lots of software engineer inside their company, would currently be struggle with. So this slide is this is a motivation of this work, and in this talk I will cover our effort to address this issue, and we disaggregate a proprietary network visibility solution to open, and we call this project TINA, the SKT Integrated Network Analyzer. So my slide is organized into three parts, and first I introduce TINA project briefly, and in this section I cover architecture and current use cases of TINA already deployed in our production network. Then next we will cover how we disaggregate the proprietary and multi-million-dollar hardware, so-called the network visibility fabric node. And finally, we cover the hardware spec, the network visibility fabric node used in TINA. So the TINA is a network visibility platform and designed for the telco infrastructure monitoring. It provides end-to-end network visibility to telco infrastructure operator to reduce the TCO by over the 50%. By using the open hardware and software approaches. This project launched at 2017, as I mentioned. And our real use case are currently three. The first one is we are monitoring our subscriber-based services running in our private data center. Second one is we are monitoring the LTE and 5G interfaces. And third one is we are monitoring the IPTV head-end. But we still extend our TINA use cases, and one of the example is we are trying to monitor the KRTCS, which means the Korean radio-based train control system. And next slide, I'm gonna cover the detail of the TINA and use cases. This diagram shows the high-level design of the TINA, and this the left-hand side, the diagram showed our telco mobile network architecture. Basically, the TINA is designed as an out-of-band monitoring tool, since the system should not impact on the production network if it fails. So moreover, this approach is still much preferred than in-band monitoring approach to infrastructure operators. So the TINA requires the optic tab or meter to copy original production traffic. Then the next, the traffic is aggregated to the network packet broker. The packet broker then distributes the traffic to probe, which are pre-processed coming low packet and see the packet deeply. And then the probe can be the IDS, firewall, deep packet inspection. But in our case, we refer the probe as a network protocol analyzer. Then finally probe export some metadata after analyzing the packet to TINA big data platform. Today's talk does not cover the TINA analyzer, but we are using and optimizing open source software such as Spark Cluster to post-process the streaming metadata from the probes, and Hadoop to store the long-term data, and Druid to store time series data. And on top of this layer, a unified SQL like a query engine is provided to data engineers, so they can find some insight from our network infrastructure. SKT has over the 200 subscriber-based services not running inside our private network. For example, the TView, security camera, and smart speaker we call the Nugu, and navigation we call the TMAP. So for this use case, so infrastructure operator they want to see the network performance of service by service in a single dashboard. So for these use cases, the TINA measure the network traffic statistics such as total traffic volume in byte and packet and number of flow per each services. Further, it also measures the TCP session performance in terms of the connection time, RTT, and lead transmission rate, something like that. And also using the gathered metadata from the probe, TINA can continuously learning the metadata from metadata, then it can detect the traffic, network traffic anomalies in data center, happening in the data center, such as MNOT traffic explosion and reduction, and volume-based DDoS attack. This can be possible. We are using the dynamic thresholding approach in the machine learning technique. And second use case, sorry. Second use case is infrastructure operator want to see the quality of the IPTV service. We call the SKB BTV for subscribers by tracking the end-to-end their communications. In order to do this, TINA measured the DNS lookup time and content location, which is usually resolved by the global server load balancer inside the IPTV head-end. And also, TINA measured the HTTP transaction performance and TCP connection time to media cache server. The third use case is we are currently ongoing project, and we TINA monitoring is monitoring the LTE and 5G NSA interfaces, including the S1 MME interfaces, S1U and S10, S11, something like that. After the TINA gathered the low signaling packet from the mobile network, then it export after processing the signaling packets, then we export some external data representation called the XDR format to the TINA analyzer. And in this use cases, the TINA measure the track the all core flow of the each subscribers. For example, the attach and detach signaling and S1, X2 handover, something like that. And we also analyze our user traffic protocols. For example, TCP, UDP, HTTP, RTP, SIP protocols to measure the performance per each mobile subscriber. Okay, now next couple of slides present how we disaggregate a proprietary and multi-million-dollar hardware network visibility fabric node, and including the network packet broker and DPDK based network visibility probe and packet recorder. Thank you. At the beginning of this slide, the network packet broker is some sort of the load balancer to distribute the tap or mirror traffic from the production network to probe based on some condition in packet. The left-hand side list shows some basic feature of the network packet broker, and currently we support from the L2 to L4 based filter, for example, MAC address and IP version 4 and 6 address and prototype and L4 source destination port number, and also network packet broker some action on each packet to the forward and load balancing and replicate. Further, we also network packet broker provides some packet slicing, packet stripping to easily the monitoring node can easily analyze the packet. And right-hand side list shows some telco specific feature requirement. For example, the network packet broker for telco use cases required to aware the GTP protocol, because all signaling message and user traffic are encapsulated by the GTP protocol. So we need to aware the TID inside the GTP. Furthermore, we also need to aware the inner headers beyond the GTP header. More importantly, the network packet broker should support the 1588 time synchronization and time stamp insert into some mirror in the packet, because the telco operators can troubleshoot the latency and jitter based on this reference time stamped by the network packet broker. So, in order to implement this network packet broker requirement, which require the hardware to be programmable and flexible, we use the P4 language to program the packet processing behavior in programmable switching ASIC due to two reasons. One reason is a target independent that abstracts some vendor specific hardware chip and MPU FPGA. So our network packet broker P4 program can be loaded on any type of the target, depending on the traffic volume to process. And another one is P4 language. P4 language is doing-yourself approaches and much flexible and versatile, because it is easy to optimize the packet processing pipeline inside hardware, and it can provide some memory optimization support provided by the hardware. Further, if the P4 compiler compile the result of the P4 compiler is some auto-generated API, so we are easily handle our P4 program. And most of all, the benefit to us is that it is easy to develop, test, bug fix, prove future features more faster than ever. So in this MPB project, we can reduce much engineering costs because the cycle of the development to deploy loop we can reduce from the 1 year to 3 months from scratch. So we developed the MPB.P4 program in P416 specification, and this package support the port and port group and ingress egress filter, and this filter can be attached to the port and ingress port or egress port, and also it supports for the load balancing, for example, normal hashing and with the normal hashing and symmetric hashing and resilient hashing, and also it supports replicate action. Further, this package support the 1580 base timestamping, as I mentioned. It supports 64-bit UTC timestamp on every packet, and this timestamp is stamped on the ESPN Type 3 header or the INT header. Further, we are support the C and C++ API to the any network packet broker agent. So any network packet broker agent can be run on top of this P4 program. Can control the P4 program. Further, we still extend and under test a new feature like metadata generation in hardware, and we also now test the GTP session aware traffic steering. Next, I'm gonna explain about the network visibility probe and the packet recorder. It is a x86 commodity server we use, and for the performance high performance we use DPDK technology. So we utilize the DPDK to pump up the load packet to application, then the protocol analyze application DPIs the every load packet, and also we leverage the receive side the scaling to load balance packet to CPU core assign, and also we use a CPU pinning technique to improve the performance. So so in this probe, we can achieve the 100 gigabps throughput and generate 5 million flow per second with 100% utilization of the 24 cores. And we also have a DPDK based packet recorder. It achieved the totally the 40 gigabps packet recording per node. So if there is a multiple node, we can increase the total traffic, total volume of the packet capture. Yeah. Now let me introduce our hardware spec we currently use. Here is the hardware the network packet broker is used. We are currently using the Barefoot Tofino-based whitebox provided by the Stordis. And we are currently support two types of the hardware. The left-hand side is a 10 gig based platform, and right-hand side is a 40 gig and 100 gig based platform, and it has 64 port. And for the packing record, we call the flow X. We support two type of the hardware form factor. The right hand side is a 4RU type of the packing recorder, but this is so heavy, is fixed to the infrastructure. So many operators much prefer the portable packet recorder. So we also developed our one portable packet recorder. The spec is as shown in this slide. This slide shows our network visibility probe. We call the software-defined visibility node. This hardware form factor is a 2R unit, and it has dual Intel Xeon CPUs, and it supports up to the 512 gigabytes RAM, and also it has 4 SATA SSD to store some log or packet file. And also, interestingly, this type of form factor has switching capable NIC card based on the Intel Red Rock Canyon ASIC chip. With this Intel-based NIC, it has some other separate management CPU to control the ASIC. And it has 4 Ethernet controller with a PCI generation 3. So it supports up to 200 gigabps to pump up to packet to the servers. Further, we also has a pluggable port module. This form factor has a 3 slot, and each slot has a 12 10 gig or 240 gig and 4 10 gig interfaces. So this form factor is already submitted to the OCP networking community, and you can find the details of this hardware spec at this link. I think that this is the last slide of this session, and this network packet broker project is open and collaboration project. So the SK Telecom and the Cool Cloud write network packet broker MPB P4 program, and also the Cool Cloud has its own production grade network packet broker agent. So we are integrate these two software things into the barefoot-based hardware platform supported by the Stories. And the Stories has some advanced program switch, which support the Telco grade features. Thank you for listening. Any question? Yeah.
I do have a question. For the network packet broker, why can you elaborate a little bit why you pick up the P4 capable chip? So if just programmability, because I know other vendor chip also have their own language-based programming. So why you not using a fixed ASIC? Why you pick up a P4-based chip? Thanks.
Good question. Actually, we are trying to use the fixed function Ethernet ASIC before developing this P4-based program. We at that time we struggle with some bug inside the hardware, SDK in hardware, and also we are struggling with the fixed function has no flexibility. We can, so for example, there is a unnecessary behavior inside hardware. For example, the layer 2 and layer 3 routing is not necessary for the network packet broker use cases. So in the engineering perspective, we should disable all these unnecessary features using the APIs. But the API doesn't support something like that. So we are moved to the P4 language to redefine the behavior of the hardware switching chip. Yeah, that's the reason why we choose the P4 language. Yeah.
I have a question about where are you going to deploy the box? Are you going to deploy on your data path, or you're going to deploy on some remote location for analytics?
For the network packet broker.
Yeah. That's the box.
Network packet broker is deploying our data plane inside our data center and mobile network cores. But as I mentioned in this slide, we are tap and meter traffic from the production network, and then this traffic going through the network packet broker. Is that the answer?
If my understanding is correct, based on your answer, it's like so from the mobile front haul, back haul, and then goes to the, like for the 4G S gateway, and then go to your broker. Is that the
Mostly we tap the traffic from the EPC core.
Okay, it's in the 4G core or 5G
Yeah.
core.
Yeah,
Okay,
yeah.
sure. Thank you.
Yeah. Any questions? Thank you for listening and having time. I'm very thanks.